All right, now we're going to pick up from where we left off, but now we're going to switch topics a little from unconstrained to constrained optimization. So to this point in this discussion, we have been talking about the theory of the unconstrained optimization. And now we want to move into the theory of constrained optimization. And so this means that we're going to add constraints. So the idea is that we want to do something like this. So minimize over x in Rn, this function f of x, subject to some constraints now. So we'll be like ci of x is equal to 0 for all I that's contained in the set of indices corresponding to the equality constraints, and ci of x is greater than or equal to 0 for all I contained in the set of indices corresponding to the inequality constraints. We are going to make some requirements on smoothness. So now, unlike before where we just had a requirement on smoothness of our objective function, we're going to require both our objective function and constraints to be smooth. So their derivatives need to exist and be continuous up to as many times as are needed to run our algorithms. And they are going to be real valued functions on a subset of Rn, and also our inequality and equality index sets need to be finite sets of indices. And we can define now the concept of a feasible set. So this feasible set, omega here, is going to be the set of points x that satisfy some constraints. So let's write it as omega is equal to x such that ci of x is equal to 0, I is in E, and then also that ci of x is greater than or equal to 0 for I is in I. And so we could then write this optimization problem up here. We could rewrite it in a very compact form. We could write minimize over x contained in this feasible set omega, f of x. So now, just like in the case where we had the no constraints, we need necessary conditions and sufficient conditions so that we can better understand what kind of mathematics we're working with here, what kinds of things are true, not true about a point that's at the equilibrium, or sorry, not at the equilibrium, a point that is the minimizing values of the decision variables leading to the minimum value of the objective function. And so we are going to have necessary and sufficient conditions. So let's remind ourselves what necessary is going to be. This is about it's necessary to be an optimum. So it's going to be that it must be satisfied by any solution of the optimization problem, meaning any minimizer. Under some conditions, and then the sufficient conditions will be the ones where we say, okay, if these things are satisfied, these are enough to guarantee that something is a solution. So these are the ones that say, like, if such and such is satisfied at a point x star, that guarantees x star is, I guess, a minimizer subject to the constraints. And I should have written that above too, that this must be satisfied by any minimizer. And we are going to care here to some extent about like, and are constraints satisfied. So we would like necessary conditions to tell us, and the sufficient conditions to tell us whether or not it also means constraints are satisfied or not. And so as a reminder, what did we have for the unconstrained case? So for the unconstrained case, our optimality conditions were as follows. We had the necessary conditions, and this was that local unconstrained minimizers have del f of x star equals 0 and del squared f of x star positive semi-definite. And then our sufficient conditions were going to be that any point x star at which del f of x star equals 0 and del squared f of x star is positive definite. Notice this is not positive semi-definite. This is actually positive definite in accordance with what we learned before, is a strong local minimizer of f. And so this was what we got for the unconstrained case. And so if you go look back at your notes, you'll see that these are required. Now, the difference with the constrained case, of course, is primarily that we added constraints. And so the fact that just like, oh, great, like some conditions on only our objective function hold, which is what this was about, that may not be sufficient for being able to tell us whether or not we've actually met, found a minimizing value of our decision variables that make our objective function minimize subject to our constraints. So we need to do more than we did before. And so far, it's not enough to just go back to these and say like, oh, I'm just going to use those again. That's not going to be sufficient when you add constraints. And so first we have to say, what do we even mean when we add constraints and say something is a solution to the optimization problem? So a vector x star is a local solution to an optimization problem with this form: minimize x over x in the feasible set, minimize f of x. If this minimizing, or if this vector x star, it needs to be in the feasible set, and there is a neighborhood n of x star such that f of x is greater than or equal to f of x star for x contained in the neighborhood, and so that's intersect the feasible region. And so as you can see, this is like different than just saying x star is a minimizer of the objective function. We're going to talk right now about solutions to an optimization problem, because when we say that, we mean that they have to not only make it so that f of x at any point except the minimum is greater than or equal to the point that minimizes the objective function, But they do that for all of the x's that are, one, in the feasible region, and two, in a neighborhood of each other. And that's why it's this sense like local, is that it's just in a neighborhood of x star. It's not like globally, it's not a requirement that everywhere f of x be greater than or equal to f of x star. It's that for all x in some neighborhood of x star, but while also remaining in the feasible region, f of x has to be greater than or equal to f of x star. So this part maybe is not super surprising, that for something to be a minimizing or a value of the decision variables that is going to be a solution to an optimization problem, it probably should make your objective function smaller than neighboring points, because or else what would that mean for it to be a minimum or a minimized a decision variable that causes f to be minimum subject to constraints? What would that even mean if it didn't mean that at least among the values of x that satisfy the constraints and are nearby this point, that this point causes the objective function to be a smaller value than do other points. But we also have more than that, because we have to make sure that our x star, this optimal value of the decision variables, or this solution of the of this problem, this optimization problem, it has to be in the feasible region. And so note also just the idea that this is not global, and that's actually really important, is that when we find a lot of optimization algorithms for constrained optimization, unless the problem is only having like a local minimum is equal to a global minimum, like what you would have with a convex optimization problem, a lot of times you're not going to necessarily get the global optimum, because many times algorithms are not designed to do that. They're designed to make sure that there is no point nearby your optimal solution that causes f to be less than it is at your optimal solution, as long as there are points that are nearby and in the feasible set. But it's not necessarily checking every single point in all of states or in all of the space of all of the x's that you could be looking at. So this is actually a really important point and distinction right here. And so here is something just to be aware of, is that a lot of times you can rewrite optimization problems. So let me call this rewriting optimization problems. So many times you are able to rewrite an optimization problem so that you can get it in a form that is better than what it was before, and still get perhaps the same decision variable value. So let me talk about what I mean here. So let's say that we look at the following problem. So say this says minimize the following function, where this function is the maximum of x squared and x. Now, this function on its own, if you were to say, okay, the maximum between x squared and x. So if I look at negative infinity to 0, then the maximum value of this function is going to be x squared, because we can see here that x squared is going to outdo x between like negative infinity and 0 in terms of making this bigger. So now though, let's look at the 0 to 1 range. So on 0 to 1, this is going to be x, because from 0 to 1, the larger value here is going to be x instead of x squared, because that's going to be a case like 0.01 squared is less than 0.01. And then if you instead then look at 1 to infinity, it's going to be x squared again. So this is an optimization problem where we sort of have which of these functions is dominating trading off. And so if we were to take derivatives of this function, like so over here, the derivative of this function with respect to x is 2x, here it's 1, and here it's 2x again. And so we can see that these derivatives are not necessarily the same at every point. So like 2x is not going to always equal 1, for example. As you And even as x is approaching, yeah, I think like that shows that these derivatives are not the same everywhere. So if we did do this though, and we said, what's the maximum value of x squared and x, or minimize the maximum value of x squared and x, the optimal solution is x star is equal to 0. And so the idea of that is that you could say like, okay, the maximum value of these, like if you did x squared, no matter where you're at here, the maximum value here is going to be 0 or above because this is squared. And then similarly on the interval 0 to 1, the since this is what's going to dominate, and then from 1 to infinity, this is what's going to dominate. So we can see that between all of these, the lowest possible value we could get for all of this is going to be 0, because that's going to be the maximum being x squared from negative infinity to 0. The minimum value of this is going to be 0. Same thing on this interval from 0 to 1. The minimum value of this is also going to be 0. And then this is going to be above 0. So the optimal solution here is x star is equal to 0. But if we want to reformulate this problem, we can get something where it doesn't have this kind of potentially problematic form. And so we could introduce a new variable, t. And so this is an artificial variable that's not in the real problem, but we could say minimize t. And so now we're going to have x and t be our decision variables. And we're going to say subject to t has to be greater than or equal to x, and t has to be greater than or equal to x squared. And so in this case, now we don't have any like minimize the maximum of the trade-off between two functions and anything like that. But if we were to solve this, we should still be able to get our optimal solution as x star is equal to 0. And then just now we'll also get some value of t as well. And so there are many problems for which you can do things like this, where you reformulate them in some way. So like if the original is not differentiable, you can reformulate it a lot of times in a way that is, by either adding extra variables or doing extra things, and then and get the same optimal solutions and stuff like that. And so getting the same optimal values of the decision variables, so getting the same solution of the optimization problem is often nice, because then you just go back to your original problem, and if you want to know what's the value of the objective function at that optimal solution, all you have to do is plug in x star into the objective function of the original problem, and you'll know what the optimal value of your original objective function is. It's really the values of these decision variables that often are what's desired. So here we're going to have a definition. And this is going to be that the active set A of x, so this is a definition of an active set at any feasible x consists of equality constraint indices from E. I'm taking this word for word from the Nocedal and Wright book, together with indices of inequality constraints I, for which Ci of x is equal to 0. So this would mean that your active set is equal to the indices for the equality constraints. So that's your E. And the union with, meaning, and you put with it all of the I contained in your set of inequality constraints such that Ci of x is equal to 0. So you can have your active set changes based on the point in the feasible set that you're looking at. So for any point in the feasible set, you can look at that point and say, okay, what is the active set at that point? And so then that will be all of the indices of your equality constraints. So if your equality constraints are labeled like 1 to 5, it's 1 to 5. And then if you have inequality constraints, then instead of looking at the times when they satisfy an inequality, you will only look at the ones which satisfy one of the, that cause one of the constraints to be satisfied with equality, one of the inequality constraints to be satisfied with equality at the point that you're looking at. And so it could be that none of these are satisfied with equality. So maybe none of them equal 0, in which case it would just, the active set is just the set of all of the indices that correspond to the equality constraints. But if some of your inequality constraints are actually equal to 0 at your point that you're looking at, then you include those as well in your active set. And this is actually a very important definition for optimization. Okay. So, so now we said that we have to think about what are our sufficient and necessary conditions for optimality when we have constraints. And so it's not going to be as simple as what we had before. And so, as we said before, we were able to just make some statements about maybe f and its derivatives and things like this at our solution of our optimization problem without constraints. But now with constraints, we have to be able to develop conditions that say, okay, I ensure that this gives me these properties. So it gives me that in a neighborhood of the point I'm looking at, and in the among the points that are in the feasible set, the value of the objective function at my current point is no worse than the value of the objective function at neighboring points. But in addition, I also have to ensure that my optimal or that my solution is in my feasible set. And so what are the things, like what are the constraint or what are the checks or the conditions which would be a certificate to me to say like, look, you've met these requirements. And so the idea being kind of, we want to find things like this, like something that's necessary, like, oh, if this will be satisfied by any minimizer, hopefully like meeting the constraints. We would like things like this, and also sufficient conditions, something like if blank is satisfied at a point x star, guarantees x star is a minimizer, we'd like to say subject to the constraint. So how do we get those types of things to get added in? So that is what we are going to talk about now. And so a lot of times things that are helpful for this are constraint qualifications. So there are many different constraint qualifications that have been developed. And so I am going to write out one of the examples of a constraint qualification. And then we can talk about what the consequence of this is, and we'll go into this in a little more depth. So a lot of times a constraint qualification used in the design of algorithms is what's known as LICQ. So this is going to be the linear independence constraint qualification. And so here is the definition of that. It's that given the point x, and the active set A of X we say that the LICQ, linear independence constraint qualification, holds if the set of active constraint gradients which is del Ci of X for I contained in the active set that we just defined, is linearly independent. And so you could go through and like do a lot of mathematics with these various constraint qualifications to demonstrate what their roles are and how people came up with these. But then what the consequence of this is that it allows us to write things like our necessary conditions. So let's write a set of first order necessary conditions incorporating this LICQ. So here's the first order necessary conditions. So what this is going to be is it's going to say, suppose that a solution, suppose that X star is a local solution of this problem. Minimize X in Rn, f of X, subject to Ci of X is equal to 0. I is contained in the set of equality constraints, and Ci of X is greater than or equal to 0 for I contained in the set of inequality constraints. I'm going to call this problem 1. So suppose that X star is a local solution of 1. We're also going to make some other assumptions that the functions f and Ci in 1 here are continuously differentiable. And that the LICQ holds at X star. Then there is a Lagrange multiplier vector lambda star with components lambda I star, I contained in the set of equality constraints and inequality constraints, such that the following conditions are satisfied at X star, lambda star. And so this says del X, L of X star, lambda star equals 0, Ci of X star equals 0 for all I contained in the set of the equality constraints. Ci of X star is greater than or equal to 0 for all I contained in the set of the inequality constraints. Let's get lambda I star is greater than or equal to 0 for all I contained in the set of the inequality constraints. And then that lambda I star, Ci of X star equals 0 for all I contained in E, union, I. And so this is what we know as the Karosh Tucker or Kkt conditions. And so this is an L. So L here, I should have defined what L is. So L in this case, as a function of x and lambda, is equal to f of x minus the sum for I contained in E and I of lambda I Ci of x. So this is the Lagrangian function. Okay, so, oh, that was not what I wanted. Where'd it go? Okay, there we go. Okay, so let's talk really briefly about what this tells us. So what this says is that, okay, I can put some assumptions on a problem that, in an optimization problem that includes constraints. I can say, okay, let's say that x star is a local solution of this. Also that the f and the ci are continuously differentiable, and that there is this other constraint qualification holding at x star, which says that like given the point x star and the active set A of x star, we say that the LICQ holds if the set of the active constraint gradients is linearly independent. Okay, so all of that has to be true. And so then in that case, we can have a Lagrange multiplier vector such that we get the following conditions to be satisfied at x star, lambda star. And these are the Kkt conditions. And so what this tells us is that we can see that this has some similarity to the ideas like what we had before, where we said like, okay, a local constraint minimizer has like these things happen. And so here we're saying like, okay, a local solution, when certain conditions hold, including some related to the constraints, then the following things hold about gradients and constraint satisfaction and so forth. And so we can see that this is sort of an analog of what we did in the first case, but that it's getting a little more complex. And so what I'm going to do next is we're going to talk a little more about the concept of duality. So about to what extent do these like Lagrangian functions contribute to us being able to think about algorithms for optimization and theory of optimization, because so far I haven't really discussed them, but somehow this Lagrangian seems important enough to be showing up in some of these conditions that say like, if some certain stuff holds and I have a local minimum, then stuff about the Lagrangian holds true. And so that might seem a little bit right now like, oh, wow, is this important? If so, why? What is the relationship of this function to the rest of this? And so that's what's going to be coming up next.